Today we are going to look at the applications of complex numbers in the case of two-dimensional vectors. So let's look at the general idea of how to do this vector analysis in complex numbers form. So the general idea is very simple. Just imagine now you have an equation of straight line where you have r equals to r naught plus at, and you know what r naught is. This is the origin of the point, and a is basically a vector pointing in one direction, and t is a scalar. So t is an increment, for example, in one unit. So you have t equals to 1, 2, 3, 4, 5, 6, blah blah blah. And a is a 2D vectors, and for the sake of this discussion, we will write a to be equals to xy. So you have xi plus yj, and this is my vector a. So when you want to use the complex number form, the idea is like this. You take the I component of this vector a, you are going to put this into real part of the complex number, and the j component over here, you are going to make it into the imaginary part of the complex number. So that is how you change these 2D vectors into the complex number notation. But here, the only thing that you need to be careful is that the I over here, this represents the imaginary part and should not be confused with the I in the vector, where this I is to represent the unit vector in the x direction. Right, so let's look at the first example. So in this first example here, I have a vector a which is written as 1, 3. So this a is the vector that enters into the equation of straight line. So I have r naught, which is the starting point, and I have a multiplied by t. So what I want to show here is how to plot this in two ways. So I'm using Octave, and there is one way, which is by using matrices. So what I do is I define the points in the x direction and the points in the y directions. So you just imagine I have a point at origin, that is x equals to 0, y equals to 0, and then I have vector a along this line 1, 3, and I multiply this by t. So imagine I have t increasing from 1, 2, 3, 4, etc. So I have many points. If let's say I have 10 points in t, then I'm going to have 10 points in the x and y direction, corresponding to the points along this vector r. And you will see that if I plot this using the complex number notation, this is much simpler. So let's go now. So now let's try to plot the vector a using the matrix form. So here we remember a is equals to 1, 3 times t, where my x-axis, I'm going to increase it by 1 unit, and the y-axis is going to be increased by 3 unit, and this of course depending on the value t. So here we can increase t in such a way that I start with t equals to 1 up to t equals to 10, and I have 10 values in between. So this will give me this sets of t values, that is 1, 2, 3, 4 up to 10. And now let's call the I component of the vector a to be u, so that the u, now this u is going to be equals to t. Whereas on the other hand, the j component v is going to be 3 multiplied by t. And now I have these two sets of numbers. So u and v are, in this case, column matrix with this sets of numbers which should be understood by in the sense that 1, 3 is one point in space, and 2, 6 is another point in space, and 3, 9 is going to be another point in space, and these are going to form a straight line following the vectors r equals to r naught plus at. So now we want to plot these points. So what we do is we are just going to plot x, y, but in this case this is going to be uv, and then I put the symbol star over here so that the points are going to be labeled as stars. And now you have these points, right? So this is a straight line. So I can just change it a little bit, and I add a dash point over here, and this is going to put these points in a straight line. Right, so now let us look at the other way to plot this, that is through using the complex number. So let's just delete this window, and now the complex number, remember I have the real part and the imaginary part, and the real part is going to be t, whereas the t, yes, and the imaginary part is going to be 3 times t. So now these are the values for the complex number now, and to plot this we are going to use the same command, that is plot z, and now we are going to label it in a different what we call that symbol, so that now I have something like this, and you will see now this is my straight line. So these are the same as the one that I get from the previous plot. So now let's go beyond straight line, and we consider a vector b, which is given in this form, where you have t for the I component, and the j, this is going to be t squared. So here you have ti plus t squared j. Now let us look at the trajectory of this vector first. So we want to plot the trajectory of this vector b. So vector b, we have the x component to be t squared. So let's just plot the vectors using matrices. So again, we have to define what is my t over here. So let's define t as equals to linear space. Let's just use 10 first. So 1 to 10, and you have 10 datas in between. And then now you have u for the I component. Let's call this as u, and u is equals to t. And then we have the j component, which is v. Now v is equals to t squared. So this is going to be t dot times t. So now you have this two sets of data, and you want to plot them. So as usual, we are going to plot them using u, v, and we shall put them in where the points is now in stars, and we put a line in between to connect them. And now this is the lines that you managed to plot. So let's now try to plot this using complex numbers. So now you have a complex z. So now before that, let's define z. Z is going to be equals to complex t dot times t, and then we shall plot this as so let me see, plot z. Now let's use the plus sign with a dash so that we connect the points, and voila, this is the line that you have. Right, so that is the two ways to refresh what we have done in example 1, where you plot the trajectory of this vector a or b using matrices and complex numbers. So now let's go back to this slide, and as you have seen here, for this vector we can actually calculate what is the velocity and the acceleration of this vector. So if you want to find the velocity, you just have to simply take the derivative of the vector with respect to time. And again, there are two ways to do as we have done it previously. I mean, for the plots, you can do it in terms of the vectors. At this will you have a ti plus t squared j. So you just have to take the derivative with respect to time, and you have here 1i plus 2tj. But if you change this vector here into a complex number form, so this is going to be t plus t squared I. So the I in this case is going to be the imaginary part of the complex number. And in this case, if you take the derivative of the complex number with respect to time, Again, you have the same kind of form, except that now instead of I, you do not have I here, because I, this is to represent the direction of the vector. So here, instead of I, you have 1 plus again 2t I. So I, now this is my imaginary part. So now this means that the velocity is given by this expression. So if you're going to plot it in matrix form, using matrices, so it means that you're just going to use this expression. So you can call velocity for the I component to be 1, and the velocity in the j component, so this is going to be 2t. Or if you use complex number, you can just simply put the velocity equals to 1 with 2t as the imaginary part. So in the plot that I'm going to show you after this, we are going to plot using the complex form. First, we are going to look at the magnitude of the velocity of the vector, and from the velocity of the vector, you should be able to obtain what is the magnitude of the velocity. And from the velocity itself, you can also determine what is the acceleration. So if you want to get the acceleration of this vector, you just have to again take the derivative respect to time once more, and you will get the acceleration equals to 2t. So let's go to the plot now. So now for the plots, we want to plot the velocity. So let's call velocity, and this is going to be equals to complex. Again, the velocity is equals to 1 plus 2t I. So this is going to be 1, and this is going to be 2 times t. So you do not have to put the I over here, because I is already taken into account, because this second term here is to represent the imaginary part, right? So let's enter, and now these are the velocities at the different points. So this is the velocity at the first point, second point, third point, fourth point, etc. And now we want to plot the vector, right? So we want to plot the vector at each point. So what do we do is we are going to plot this on the complex plane. So now if you can just imagine, on the x-axis over here, this is the real part of the z, which is vector b. So the z, as you have seen here, z equals to complex t times t. This is the points in the x-axis and the y-axis. So now in order to plot the velocity at each point, you have to give a position for where you want to plot this. So on the x-axis, this is going to be the real part of the complex number. So this is, let's call this as xx, and this is the real part of the complex number. So this is real z. Whereas on the y-axis, and this is the imaginary part, so this is going to be y, and we put this as imaginary z. So here, what we are going to do is we are going to plot this velocity at this position. So you're going to plot, let's say, 1 plus 2i over here at the position 1, 1. So 1 is the real part, and 1 over here, y is the imaginary part. And then you are going to continue doing it, 1 plus 4i. This is at the x equals to 2, and the imaginary part y equals to 4, and you go on. So in order to plot this vector, you are going to use the quiver function. So I'm going to write here quiver. So this is x, y is the position where I want to plot this points. And again, as we have done previously, we have the u and v. So u is the x component or the I component, and over here this is the imaginary velocity, which is the j component of the vector. So now let's just enter, and you will see this is the resulting plot that you have. So here we should also put a hole on, and we plot again the z, the z-axis, so the z complex number or the vector. And here, so you have the green line. If you see, this is very fine, but this is the green line to represent the vector b equals to ti plus t squared j. And at each point, you have the velocity of at the position. Right, so here you see this is a starting point, so the velocity increases as t increase. Right, so this is the plot using the complex number. We have plot this vector b using matrix and also using complex number. And when you use complex number, what we have done is to also plot the velocity on top of the points. So let's just do one more last thing before we end this example. So now we want to plot the acceleration. So let's say just call acceleration, and as we have found just now, acceleration is going to be equals to 2I, right? So let's just put complex. So the real part is 0, so the imaginary part is going to be 2. So here you can enter. So you have this just one value, because there is no dependence on t. And in this case, it means if I plot this acceleration, my vector is all going to be pointing in one direction, that is towards the along the imaginary axis, that is the y-axis. So now let's just plot this to be complete. And again, we are going to use the quiver. So here let's call this as h2. So let's quiver, and again, this is the position that I want to plot. It is going to be at x, y, y, and the real part is going to be the real part of the acceleration, and the y-axis is the imaginary part of the acceleration. And now you enter and you plot it, and here you see there is a tiny arrow over here, and this is my acceleration. So if you just imagine you have something like this on a curve over here, so the velocity is going towards this direction, but your acceleration, right, is going to be only on one direction, towards the along the imaginary axis. Right, so that's it for example number 2. So now we are going to example number 3, and we are considering a particle moving in the xy plane as a function of time, which is the position in the xy plane is represented by this complex number z equals to I plus 2t divided by t minus 1. So the first thing that we are going to do is to plot the trajectory. So you want to know how does the trajectory looks like. But of course, you can do this by hand. That is, first you insert t equals to 1, t equals to 2, t equals to 3, etc. And you have the position of this z right in the xy plane. Or as I will be doing, we will use a plot to show what is how it looks like. Then when you are given this complex number, you should be able to find, in this case, the velocity of the particle. So we know that the velocity is the change of the position as a function of time, and here you just have to simply take the derivative of z with respect to time, and you should be able to get this expression, which is minus 3I divided by t minus I squared. So this is the velocity. So you have a dependence on the direction, and at each point you will be able to find the magnitude of the velocity. So the magnitude, of course, is simply taking the more absolute value of this velocity. And you will remember that the velocity in this case can be obtained by taking the square root of the complex number, which is now dz over dt, multiplied by its conjugate, right? So if you do that, then you will be able to get 3 over t plus 1. So this is the magnitude of the velocity at each point. So now let's look at the plots using Octave, and we are going to plot the trajectory, and then we'll plot the velocity, and we will also plot the acceleration. But before that, you need to do some mathematics. You need to take the derivative, the second derivative of z, in order to find the acceleration. And from there, you should also be able to find the magnitude of the velocity of the acceleration at each point of t. Right, so now let's go to Octave. So now we are in Octave again, and we know that we have the position as a function of time t, and now we need to give a value for t. So you need to give an array of numbers. So in this case, we use t equals to a linear space of 1 to 10. But let me just use a smaller sets of data. So now you have t from 1 to 10. You have 10 sets of data here. And now z is going to be a complex number where the real number is now 2 times t, and the what we call that, the imaginary part is equals to 1. So this is a numerator, and this is a numerator, and you'll be dividing this with another complex number. So this is going to be complex t minus I. So t minus I, this is the denominator. So here you will see that I need to put a dot in between here, so that this value you have a dot divided by this one. So basically this is telling the code, the computer, to evaluate each point and as it is, and not to lump hold them into one numbers. So when you do that, you will have this sets of z values, and now you want to plot this. So let's just plot z with the symbol plus and minus, and then you will have this graph. So here you see, here you have a very you start with this point over here, and if you want to convince yourself, you can just put t equals to 1, and you will be able to get z, the real part of z is equals to 0.5, and the imaginary part is going to be 1.5. So it's going to start from this point, and it's going to move to this point and slowly go down to here. Right, so I just want to show you the importance of, if you are really into making plots, or you are doing some analysis, it is very important to have small data, a small increment in t, because if let's say now I change t is equals to 1 to 10 again. Now let's just take 1 to 10, but then I have 100 datas in between of these numbers. So this is going to be a huge data, right? Not that huge, but then hundreds columns. Okay, and then now I'm going to calculate the z number now, and we are using the same expression in this case, complex 2t minus I plus I divided by t minus I. So now you have another set of numbers, but just for the record, if you do not want all these numbers to appear here, you can just put a semicolon at the end of the sentence, and you will press enter, and you see there is nothing that comes up. Okay, so it will store in the information, but it will not appear on screen. So now you want to plot this, but let's just put on hold the previous plots, and now we plot again the trajectory of the complex number z, and you will see that the plots will look like this. So here is the plot. This is the plot. So this is the one with 100 datas in between 1 to 10, t equals to 1 to 10, and this line is the one that you get when you have only 10 sets of datas. So here I just want to show, it is very important, if you are really into making nice plots, then you have to look at the very small increment in t, or in any variables that you're considering. Okay, so let's just close this one, and now we will be plotting zx. So this is the plot that we want to see. Okay, and now we want to plot the acceleration. Before that, the velocity. So we will plot the velocity. Let's write velocity equals to, as we have found just now, the velocity is going to be equals to minus 3i divided by t minus I squared. Okay, so we will ask the computer to compute this, and then now we are going to plot this velocity. Remember, this velocity, there are values, these vectors at each point in space. So now you have many data, and you want to plot this data to coincide at the particular point. And what I mean is, let me just show you this data. We'll just wait for a while. Right, so here this is the first number, 1.5 minus 0i. So this is the first velocity that you will get at t equals to 1, and then you will have a change in the direction of the velocity as a function of t. So, and you want to plot this at the first point. So how do you do that? You are going to define the position that is xx. So this is the real part of the z value, z complex number, and of course you have many datas again. And y is, let's just call it y. You can actually call it any names you want, right? But in this case, to make it simple, I just call it yy, and this is the imaginary part of the complex number z. And now I'm going to plot the vector on this point. So I'm going to use h equals to quiver. So this is xx is the point in the x-axis, yy is the points in the y-axis, and I'm going to plot the real part of velocity and the imaginary part of velocity here. And let me just enter. So you will have the plot right after this. And here, so here this is the plot of the velocity as a function of time. So here you see the particle is starting from here at this point and is going towards this direction, and you will see the velocity changing in direction slowly as a function of time, right? So now we want to plot the acceleration. So here acceleration is going to be equals to minus 6i divided by t minus I to the power of 3. So let's ask the computer to compute this, and we are going to plot all the data that we have, that is the z, which is the position of the particle, the velocity, and the acceleration, all in one graph. Right, so now let's just plot this h2. I just call this as h2. This is the quiver x, y, y, and this is the real part of the acceleration, and imaginary part of the acceleration is next. And I will just enter. So here you will see this is the acceleration. So now let me just put in the others. We are going to plot z, and oh yeah, before that we should put hold on. That is, if we want to make sure that the previous plots are retained and not to be overwritten when you plot new graph. So you will plot again. Let's plot again. Plot z, and we are going to plot the velocity, and we are going to plot the acceleration. So let's see the resulting graphs. So here you have the line in the orange. This is the velocity. You can no longer see the position of the particle because they are covered by this velocity, the arrow that represents the velocity of the particle that is moving nicely along this line here. And the plot in red color here, this arrow in red, is the accelerations. Okay, so this is acceleration actually with direction, as you can see. So if you want to find the magnitude, then you have to take the absolute value of the acceleration. Alright, so basically that is how you do the plots in Octave. We have seen how to plot the position, the velocity vector, and the acceleration vector, and all this is just to mainly to give you kind of like a graphical interpretation of the equations that you see. And sometimes when you see the equations, and you'll be imagining, you know, what is this all about? So sometimes it is very nice to put this into graphics, and I hope this sort of helps you to appreciate, you know, what you are doing. Alright, so thank you very much, and I hope that you have enjoyed the video.